So real quick, again, for the people at home, the updated homework sheet is now up on Canvas. And what was the other thing I was talking about? Just to remind everybody, office hours and locations. And all you got to do, if these don't work, is email me and say, hey, man, I can be there at this time, this time, and this time. Does any of that work? And I'll pick which work time works for me. It's crazy. Okay. So anything homework? Anybody trying the homework out? As always, I know a few of those problems get weird. So when nobody asks questions, get a little worried. Yeah.
71
by 5. Oh, okay. So they give you that it's a box, and the length is twice as long as the width. So you already know the players, and you know which one should just be a single letter. What players are there? What are the parts of this problem? From the first sentence, I know the parts.
There's the
The length and the width. Okay, those are the two in English that I need to give math names, right? So which one is going to just be a single letter? You don't have to use X. You can use something more descriptive.
The width.
The width. Why the width?
Because everything depends on.
Beautiful. The length is twice as long. The height is 2 inches greater. So then we got a third player, the height. So we got length, width, height. So the width, what do you want to call the width? Does everybody see why the width needs to be given a name first? Because if I know the width, I immediately know the length, and I immediately know the height. So I've got to give it a name first. So what do you guys want to call the width? W. Holy shit. All right, I love that, right? And the funny thing is, sometimes you guys don't realize there's nothing special about X. Not a damn thing. There's a history as to why we picked X. We didn't just pick it out of random. We didn't pick it because X marks the spot. There's a history as to it, but who cares? In the end, it could have been anything that we picked. We just happened to pick X. So yeah, I'm going to call the width W. So then what's the length?
2W.
So you're going to make a list, right? Width, length, height. Width is W, length is 2W, and the height's going to be?
W plus 2.
W plus 2. Kick ass. Not W times 2, correct? This is 2 inches greater than. Not twice, right? Like the length is. Okay. What's the formula for the volume of a rectangular box? Length times width times height. Yeah, it's just the 3 dimensions multiplied. It's crazy. So then you can set up an equation. Are you guys with me? Now, this question came up before. You're going to end up with an equation. Normally we would factor it. We'd get equal to 0, we'd factor it. You can't factor this one directly because it's going to have a cubic. So you're going to have to use synthetic division, which is why this word problem is in this section. Do you guys see that? It's kind of crazy. So when you encounter a word problem, if you know what section you're in, you probably know what procedure they want you to use. Okay, you guys all with me? It's kind of crazy. On a test, you ain't got that shit too bad. But so whenever I give you a word problem on a test or something, and you end up with a quadratic, beautiful. Get it equal to 0, factor it, quadratic formula it, whatever. If you have a higher power than 2, you might either need to group, you hope, or you got to use synthetic division. So you're going to have to use synthetic division on this one. Okay. Yes.
So how would we set that up? Would we put like a 2 and then synthetically divide it, or because it?
Well, first off, we got to get the equation, right?
Mm-hmm.
So, all right, let me get everybody to the point where you at least have what you're supposed to be working with. So you make a list of all the players, length with height. And we call the W, we call the width W. So the length was 2W, and the height was?
W plus 2.
And I know that the volume is length times width times height. And I just shove shit in. Dude, what was the volume?
192.
192. The length is
2W.
2W times W times the height.
W plus 2.
You see when you multiply this stuff out, you're going to go to cubic. Everybody see that?
Yeah.
And you're going to have some missing terms. 192. So one thing you can do is just do this, 2w squared, and then distribute that. What are you trying to be? 2? So you go 192 equals 2w cubed plus 4w squared. So everybody's cool with that? So one thing I always look for when I have an equation, I can always divide both sides by anything I want to except 0. So if I ever notice that all the numbers have a number that goes in evenly, first damn thing I do. Wouldn't synthetic be easier if the numbers were smaller, for example? Almost everything we do would be easier if the numbers we work with were smaller, correct? So anytime I can make all the frickin' numbers smaller, shit yeah. So I have an equation, I could divide both sides by 2, which would be really smart. What do I then want to do with what's left?
Take out I wanna say 2w squared.
No.
Oh,
Subtract.
Yes, why subtract 96? Why?
So it's
Because then you can-
0, just solve.
Because I can't get w by itself. I can't get all the w's in one term, so I've got to do the other approach, which is try to get equal to 0 and factor, correct? And now here's where I'm going to get some people charge ahead and do this somehow using just 2 parentheses. That doesn't make any sense though. It's not a quadratic, right? The middle term doesn't have a power that's half the first term. It's not going to factor like that. So you have to use synthetic division. Can I group that?
No.
Shit, no. It doesn't have 4 terms. I can't group that. Do you guys see that? And again, that's why they put this word problem in this section. Because this is where we learn, if I remember correctly, this is where we learn long division, synthetic division. Okay. So could you make a list of possible rational roots? Could you then start trying some out? Shit, yeah. Okay. You guys all with me? So everything in this problem was exactly the way we've done stuff like this before, but before we would have had like w squared plus 2w minus 96. We would have factored it. Now they're just saying, all right, you've learned some other ways to factor, so let's throw some of that at you. Okay, maybe. So no matter what the word problem, if I end up with something like that, I'm going to try synthetic. Because I can't factor that directly. I can't use quadratic formulas. Is everybody cool with that? You guys see, I cannot use quadratic formula. I can't. Now, real quick, you guys all cool with that? I'm going to take all this away, is that right? Okay. Can you use quadratic formula on this?
Yes.
Yes, quadratic, check. Can you use it on this? You ready? Yes. Why? Is this quadratic in form? Is the middle half of the first?
Yes.
So watch this. How would quadratic start here? What equals negative b? What equals?
X.
X. So half of that, right? So how would quadratic start here?
X squared.
X squared equals negative b plus or minus blah, 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 blah. So why can't I use quadratic on that? Because the middle power is not half the first one, right? Maybe. So there's an idea called quadratic in form. The reason quadratic works on these is because if you cut that in half, you do get, if you split that up, you do get this type of thing, right? So you could potentially make it x. And what about this? Couldn't you make it x squared? It's just that the nut is not factorable directly. What goes here is going to be gross. It's going to be the results I get from quadratic formula. Okay, maybe. So I really want you to know, nothing special about this problem. You set it up exactly the same. It's just the equation we end up with, I can't factor it, so then I have to use something like synthetic. When I say I can't factor, I mean I can't factor that directly. I can't just do it with some of our method. I have to use synthetic, which is a new way to factor something. Okay. All right. Anything else that I can just go on and on about? Any other problems from homework? Okay. All right. Let me try to get some stuff back here. Lena. I can almost read this. Shanad? No. Yes. Is it Shahad or Shahad? Lena, just there. James. Hold on, hopes for James. Diane, I saw. Isabella Revelis.
Yes.
Alexis.
I do.
Okay.
I have my chemistry.
All right, guys, so if there's no more questions from homework stuff, you could also just ask general stuff like, hey, man, what the hell did we do last time? Right? That's a perfectly acceptable question.
I had a question. So when we do like the possible rational ratios,
Yes.
does that kind of tell us like what our answers are gonna look like? So like say like the positive answers, it says like 2 or more, so our answers would have to, or 2 or 0, so our answers would have to be like 2 positive numbers. Does that make sense? Like,
Oh.
does it kind of tell us like, kind of check us? Like,
Well, here's the weird thing about complex numbers. It's a little more difficult to figure out if a complex number is positive or negative. Does that make sense? Because it's got parts to it. So 5 plus 3i, I think we all agree that that's probably positive, correct? But what about negative 5 plus 3i? Is that positive or negative? Do you see what I mean? So that's why it says you have 2 real positive roots or no real positive roots. And then they're complex, and then we can't really, there's a way to do it, to identify a complex number as positive or negative, but we haven't talked about that yet. It's a little bit more out there. Is that all right? So, okay. All right, so let's do this. I have this feeling, before we get into new stuff, or get back into, yeah, we're gonna get into chapter 6 today, but yes.
Oh, I was just gonna ask, can we, kind of do like an example problem of the slanted
Yes,
asymptotes? Because
so-
I was getting into 5.7 and I wasn't really.
It's like I planted you there. All right. So let's do an example slant asymptote problem. That'll also include a review of like vertical asymptotes, all that kind of stuff. We're all gonna be adventurous, and Jeff's gonna make a problem up on the fly, and we're gonna see what happens. Oh boy, this could get exciting. Let's see. Give me a minute. Oh, I mean it the other way around. Shoot. Hold on, guys. Oh, let me do this. Okay, that'll make it easier. Okay. Yeah, let's just keep this nice and straight. Okay. So let's say the instructions just say graph this. I would also say, and I think the book does too, find the intercepts and the asymptotes and the so forth, and then graph, right? Can anyone tell me anything that you could do with this to get started? Yeah, so start factoring this stuff. So the bottom is x plus 4, x minus 4. What about the top? It's 2 terms, so it could either be squares or cubes, right?
Mm-hmm.
This is the way you should always look at something when you're thinking about factoring. You should say, okay, 3 terms, it would be, or like surefire or something, right? Like put the 2 parentheses, or you find numbers that add to be something and multiply with something, blah, 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 right?
Mm-hmm.
4 terms grouping, 2 terms, squares or cubes. So which one's the top, obviously? Cubes. How do you start cubes? What do you put down first?
You have to do a little dude.
Thank you. The
And
big
then
dude.
that's
So
big dude.
infrequently people just humor me and just say that. Little dude, big dude.
That's
Right.
actually how I remember it.
Yeah. So little dude, big dude. And the nice thing is when you have a visual anchor like that, it might connect to the next memory of what to do, right? So little dude, big dude, and your brain might go, okay, here's what goes into each one. Okay, cool. So what's going to go into little dude?
X minus.
Yeah, 1x, 1, 1, and then the same sign. So there were 3 x's, what has to go here?
X squared.
The other 2 has to go at the end. 1 is just always 1. So the 1, 1, and then 1 squared is 1.
Mhm.
And then what's the middle term? That's the one that always confuses people.
Opposite of the first term.
Opposite.
X.
Yeah, 1x. I love it. Kick ass. Okay, let me stop for a minute. And it only makes sense to factor because where do vertical asymptotes come from? Let's find those first.
The vertical asymptotes.
Where do they come from? Yeah, why? Why do the vertical asymptotes come from the bottom? Because the bottom can't be 0. And the vertical asymptotes are walls that we set up to tell the function you can't go here. You with me? I love it. The more you understand why, like, for example, why vertical asymptotes exist, the more you don't memorize, you just do what you deem to find. They exist where we're not allowed to go. Okay, what about this? A fraction, oh, the bottom can't be 0. Of course that's where the vertical asymptotes live. Because their job is to say, you can't go here. This is weird shit happens here, right?
Mm-hmm.
So my 2 vertical asymptotes are what?
X equals 4, X equals negative.
All right, big time brownie points to Sarah for making them equations. Kick ass. Because they are lines, you have to give me an equation. Kick ass. What about horizontal asymptote? Now here's where we get to weird stuff, right? Let's do that in a minute. Horizontal asymptote, not really, but we'll do it in a minute. Tell me the intercepts. Take a minute, figure out the intercepts. It's not 3 really, it's only 2. But forgot which way was which. How do you find the x-intercept? How do you always find the x-intercept?
Well, you have to, the intercepts are the top.
Sure, because intercepts are always the values that make the outcome 0. That's what they are. So set y equal to 0. What's a better way to say that? The outcome must be 0.
Mm-hmm.
And what's the only way to have a fraction equal 0 is if the top is 0. You with me? If the top is not 0, there's no way in hell that fraction is equaling 0. What do I divide 2 by to make it 0? You can't. All right. 2 over 18 trillion is still not 0, correct? Okay. So the only real intercept we have is
1, 0.
1, 0. That's the only real x-intercept. So now I want the y-intercept. So be really careful. When I say find the intercepts, I mean all of them, right? So some of you guys just do the x-intercepts, but I inherently want the y also, right? So how do you get the y-intercept? That one's nice. Y-intercept is almost always easier
Mm-hmm.
because to get it, you just make x 0.
Mm-hmm. Negative 1.
1 over 16, right? Okay. So 0, 1, 16. All right. Let me stop for a minute. All right, so
So
now.
you don't have to find the other one?
Say again?
So you don't have to find the other one?
I really want you guys to I showed you a weird little thing about there's a real answer and then there were 2 imaginary answers for every like sum or difference of cubes.
Mm-hmm.
Every sum or difference of cubes is going to have 1 real answer, 2 imaginary. Always. That's an immediate thing you should remember. So if I'm asking you to graph something, I'm never going to ask you to graph a function using complex numbers. That's not the level we're at. Because that's where you get the weird freaking color shit. It's a little bit later, right? Let's stick to 2D for now, right? So when you have a cubic up top, you're just going to get 1 real x-intercept. It's going to come from the little dude. Can you guys all see the big dude's going to have imaginary answers? How would you tell? How could you tell just by looking at it? Well, you got to do a little something. That this is only going to have complex answers. So remember, what part of the quadratic formula is under the square root?
The
Negative b plus or minus square root of b squared minus 4ac. So if I do b squared, 1 minus 4ac, 1 minus 4 is negative. I'm going to get 2 complex roots then, right?
Mm-hmm.
Do I have to worry about them when I'm graphing this real function?
No.
Nope. Does that all make sense? We know there's 3 solutions. We know there's 3 x-intercepts, but 2 of them are complex. We're not dealing with colors yet. Yeah.
So if it was on like a test or quiz, we wouldn't have to do the two imaginary ones, like when writing an
If
answer?
the question was find the intercepts, I'm always talking about real stuff when we're graphing, so you could ignore that. If the question was find all the zeros, right? Different question, but you all have seen that problem. Then I'd want the complex answers also, right? You use quadratic formula. I'm not going to waste time here because those are not real, and I'm never going to make you graph a function using non-real inputs. You're welcome. Yeah, that's a little bit further down the road. If you stick with math, it's like math. When's the first time I had to do that? Math 600 something? I can't remember. Anyway. So now let's focus on, there is no horizontal asymptote. Because what situation am I in? The top degree is higher. What does that mean? The top is
Getting bigger.
growing faster than the bottom. So the thing I'm dividing is getting bigger than what I'm dividing by. It can't keep up. So it's going to go to infinity. But it's not just going to go to infinity however it wants to. It's going to go in a very prescribed manner. Does anyone remember how to find that?
You have to get this.
So real quick, if I divide this, will I get like a whole number part?
No.
No. If I divide this, will I get a whole number part?
Yes.
Right? Isn't that 1 2/7, 1.28, whatever the hell that is? You guys all with me? So look, here's the similar idea. Higher degree on top, I can long divide it, and I'm going to get a whole number part to it. All right, so let's long divide this thing. So basically, when you have a slant asymptote, and let's do this. What are the three situations for horizontal asymptotes? The top degree could be smaller than the bottom. So like x cubed over x to the fourth. What would the horizontal asymptote be then?
0.
Y equals 0. Kick ass. Everybody with me? Because now the bottom is growing faster. The thing is dividing by more and more. It's going to go to nothing, right? Top can't keep up. The two are the same. We just saw that a minute ago. The two are the same. Then it's just a ratio of the coefficients, right? The leading coefficients. Are you guys all with me? It's like the one we saw earlier, that was 1/2. You guys all sort of with me? Okay. And this situation is always going to lead to the thing we're all going to like the least, understandably, is the slant asymptote. Bless you. So, I'm sorry. I'm not going to point out who it was, but somebody just went, no. Okay, well. All right. By the way, remind me, horizontal asymptotes, when do they kick in? I don't give a shit about it. I can cross through them all day until what? X gets really big. That's why the book calls them end behavior sometimes. Y'all with me? Because end behavior is about what happens when X gets really big. Horizontal asymptotes kick in when X gets really big. Okay. So let's see what this thing does. What do I have to be careful about when I set up this long division?
The fact that it's missing terms.
Yeah, what's it missing?
X squared and an X.
Yeah. Great problem, Jeff. All right. So help me out. How do we get started?
X.
Oh, x squared times what is x cubed? X times x squared is x cubed. I always thought that was funny because I'm like, of course it does, because that's why I put that there. That's a way to make sure you're on the right track. These better be exactly the same. X times negative 16x, so that goes over here, Jeff. Good job, buddy. And then I change the signs, kick ass, or subtract. I love it. So these cancel. I got no x squares. This is 16x minus 1. And do you see how do I know I'm done there? I still have to write the remainder, but how do I know I'm done dividing?
Because x cubed is bigger than 16.
X squared
X squared.
is bigger than x, is a higher degree. Yes?
I have a question. Why did you put the 16 under 0x and not 0x squared?
Oh, why did I put it here? Because it's like terms here.
Oh, okay.
That's all. And I put this here in case I got an x squared term, so I had a like terms place to put it, but I didn't get an x squared term because this guy's missing stuff too, right?
Yeah.
So I put those there just in case I get stuff that needs to go there.
Okay.
And then if I didn't, I don't care. It just, all right.
Okay.
So this will be plus, now really always, it's kind of funny how much I say this. but I really want you to understand this. What did I say horizontal asymptotes are all about? When do they kick in? When x gets really big. Kick ass. Tell me, when x gets really big, what is this guy doing? Always, this is cool. You could, first, I'm going to do this to you. Ready? That's its own little problem. Isn't the top degree lower than the bottom? So what situation? That's going to go to what? 0. Here's the great thing about that. The remainder will always go to 0. Because when do you stop? When this degree is smaller than that degree. Do you guys understand? That's why your slant asymptote will always be the whole number part. Do you guys see how that's the whole number part? Plus a fractional part, correct? If I divide 9 sevenths, don't I get 1 and 2 sevenths? 1 is the whole number part. Don't I get x and this over this? Your slant asymptote will always be the whole number part of your long division because the remainder will always go to 0. Does everybody see that? This is definitely going to 0 because the bottom is growing way faster than the top is. All right, let's try to put this together. Okay. Maybe I can incorporate different colors. That would be amazing, Jeff. All right. So now we got all kinds of information. Let's see. What do I have? Our asymptotes go out to there, so I want to go at least to 5. Yeah, the biggest x values I got are 4 and -4, so I'm going to go out to 5. I'm not going to figure out my y scale yet, because all I know so far is the y-intercept. Let's see if we need some more information. Let's set up our vertical asymptotes. -4 and 4. Cool. Now, I am going to put in there this. So my slant asymptote, y equals x. I'm going to put a slant asymptote in here. Okay. So let me see, real quick. Once you see what I'm about to do, I'm gonna do a really rough sketch over here, right? Make sure this thing picks it up. I love you guys so much. I'm like, this is so great, Jeff. I'm so happy I took this class. There's checks and balances. I know it feels like there's a billion things to memorize, but remember, I am going to ask you each of these separately, right? I've given you a way to know how to tell what situation you're in for the ha. The va is always the same, very single-minded, right? So real quick, just a rough sketch of what's going to happen. I'm going to put in here y equals x. Do you guys see that? Normally horizontal asymptote's like this. This was a slant asymptote because this y equals x. Do you see how the function is either going to live here or it's going to live here? You guys see that?
Yeah.
Can you guys all see that? For real, okay. So for example, it could either be this, whee, or it could be this, just in this one little section over here. Whee. Those are the two options because I see the walls, correct? I really want you to see how once you get the walls down, it completely limits what's happening because I think sometimes students feel like, holy shit, this thing could be anywhere. How the hell am I supposed to do this without doing the calculator and copying, Jeff? Because you got walls. Those are the only two options. Yeah.
So for the slanted asymptote, the x that we got is just that's
this here, right? Y equals x.
Whatever it is, the slope
That's the asymptote.
of, well, that's the slope of the asymptote.
Oh, sure. The asymptote has a slope of 1. Sure.
Okay.
And a normal horizontal has a slope of 0. Yes?
Yeah.
This one just has a different slope.
Okay.
And to really blow your mind, your asymptote could be parabolic, but let's not go there. Yes?
Why was it easy to see that it would only be on those?
So it's got to approach that wall, correct? And it's got to approach that wall. So it could either only be here because it has to approach that wall and it has to approach that wall, correct? Or it could be up here. Yes?
But why couldn't it be on the other side of the other wall?
No, okay. 1, 2, 3 regions, yes? So in this region, it could either be up here or down there. What could it be doing in this region? Well, it could be doing this, it could be doing this. It could be doing a lot of things in there, right? It could look like that, it could look like that, it could look like this. So we got to figure that out.
Do we have to do it for all 3 regions?
Oh, yes, I'm sorry, yes. It took me a second to process what you asked. And over here, the same idea, right? It could either be here, shouldn't be going back on itself but 2, or it could be down there. All right, so how the hell do I determine? Well, do you see how if I just plug in a 5,
Yeah,
I can see if it's here or there?
Okay.
Do you guys see what I'm saying?
Yeah.
And over here, if I just plug in a -5, I can see which side it's on, right? In the middle, we're going to need some help. Now, what did I forget? I forgot my x-intercept. Let's set up our, well, let's see. Did you keep track? Which things do I want to know? I haven't drawn in my y equals x, have I? Because one of the last things you determine is your y-axis scale. Why? What did we just say we need to know the value of? I need to know the output at 5. Well, if that's 80, I don't want my scale to be 1, 2, 3, 4, 5, right?
Mm-hmm.
So let's figure out what is f of 5. What's that going to be? So it's a little easier to use this one this time. So 124 divided by 9, which is approximately 14. Is that right? Somebody can help me out. It's 13 point something. I think.
13.78.
So for us by hand, 14 sounds good. What else did we want? -5, right? Same idea, same reason. So f of -5. Let's see, I mean, -126 over 9 again, which again is about -14, I think, right? Actually, I think it is exactly, is it? No. Yes. Is it exactly 14? -14?
Yep.
Look at Jeff knowing math. Let me stop for a minute. Go ahead.
Where did 124 come from?
Oh, when I plug a 5 in, I get 125, right?
Okay, yeah.
Yeah, 5 cubed. Yeah.
Okay.
Okay. Yes.
Why did we pick 5?
So again, before I can set up my y-axis scale, I got to figure out what values do I need to know. So if I just think about what's going to happen, I need to know. So this is 4, correct? That's where the vertical asymptote is 4.
Yeah.
So if I knew what it was doing at 5, I would know if it was up here or down there. So again, all right, let me try this again. I'm going to graph this one again. So what I'm doing over here is just a rough sketch, just to get a feel of stuff, right? So I know I have a asymptote at 4, and I know I have an asymptote at -4, and eventually I'm going to have a y equals x asymptote. Is that cool? Mm-hmm. Y equals x is a slant asymptote. Is that all right?
Yeah.
Okay. So I really want you guys to see this. It could either, the function up here above 4, it could either be here or it could be here. Now, to be honest, we actually already know what it is. Because what's the only way it could be here? It would need to have a x-intercept there. And the only x-intercept we have is at 1. But there's not a damn thing wrong with just figuring out what it is at 5 anyway, right?
Mm-hmm.
Is that better? Trust me, I understand. The last thing I do is figure out my y-axis scale because I need to know the points that I need. What are their outputs? I can't set the scale up until I know those outputs. You guys all with me?
Mm-hmm.
Normally, the points I'm going to want to use are points that are kind of around my asymptotes. Almost always. Right? So even if you didn't do this rough sketch, you would probably know you want to plug a 5 in and a -5 in to see where the hell it is, right? Yes?
So on the quiz, if it asks, like, use your own points to plug into the equation, you would just choose the points that are closest to the vertical.
Normally, yes. I'm not going to say a blanket. Yes. Because sometimes, just remember how sometimes you want to know how deep something goes?
Yeah.
So it could be in between a couple things. Are you with me? Yeah. Okay. Like if I had two x-intercepts, I might want to use a number between them. Okay, maybe. Okay. So pretty cool with what I've drawn up here so far. I haven't really drawn much of anything because I haven't been able to put any y stuff yet. But now I know what are my biggest outputs that I kind of need to show. 14s, negative 14, 14. So what's a good scale for the y-axis maybe? 2, maybe 3, 4. All right, so let's see. Let's use 4. What? 4, 8, 12, 16. I don't want to get too big because, Jeff, you can do it, buddy. What's my y-intercept? 0, 1/16 exactly. So I don't want to get my y-axis too big of a scale. Okay. So now I could do everything else. Now I can plot my y-intercept roughly. All that really matters about the y-intercept is that it's up there. What's it going to do at 1? What's the multiplicity of this? So it's odd, so it's going to go through. Can you guys all see the shape it has in the middle section? Can anyone describe the shape it has in the middle section? Looking at the middle, right in here. What's it got to do? It's got to go through the x-intercept, and it's got to go through that y-intercept. So it's going to be cubish or cactus. I love it. Is everybody kind of with me on that? Become a thing. Okay. It had to go through the y-intercept, and it has to go through the x-intercept. That's the only damn thing it could do. It can't do this because there's no other x-intercept to go. It can't do this because then it wouldn't hit this one, right? I mean, it's got to go through this one, so it would have to go through. Okay. I can also now draw y equals x. That's my slant asymptote. So for example, I can draw, does it go through 4, 4? I just pick a couple points, and negative 4, negative 4, and then I can draw this asymptote. Let's see if Jeff does an okay job. Not too bad. It's a little, it's pretty good for me. And then we got f of 5 was what? What was f of 5? Now can you guys, again, I totally get that this is brand new to you. Do you guys all see it? There are 3 regions to this. There are 3. There's this region. So it could either be down, see it? It could either be down here or up here. How do I already know it can't be up here? What's missing that I would need? X-intercept. So I know it's down there, but now I know a little bit better. F of negative 5 was negative 14, which is right there. So now it's doing something like, this is a little bit weird. It's a little bit weird, but it's doing something like, let's see, it doesn't have to get way up there. So it's doing something like this. Whee. And then if I continue this, whee. Yes?
So negative 14 was another intercept?
Negative 14 was just a point we found. Just so I can know what it's doing over here, right?
How did you know that you had to put it near negative 5? Because you went.
It just had to be near negative 4, right?
And the slant, how did you know it was negative 4, negative 4?
Oh, it's y equals x. So what are the, if I want to graph y equals x, what points does that go through? Y equals x. 1, 1, 2, 2, 3, 3, right? So look at my y-axis scale is by 4s. So I just plotted the 2 easiest points, 4, 4, and negative 4, negative 4. That's all I did, right? Is everybody cool with me? Just got to graph y equals x, and I can do any 2 points I want that it goes through. And obviously it goes through the origin also. You guys with me? So just got to graph y equals x, and I just use the scale that I've got. What was f of 5? 14. So that's right here. So again, it's doing this kind of thing. Whee. And then what do you do once you've got that done? Then you graph it in your graphing calculator. And you resist the urge to change. If it's basically this, you leave it alone. If you're like, well, he does this little wobble, I don't want to see that shit. Because the only way you could have known that is if you saw it in the calculator. I want your graph to match your work. So you will get more points if your graph is wrong because your work is wrong. Does that make sense? One thing I'm grading you on is, can you translate your work to the visual? And if your work and your visual are not connected, it's It's not good. You lose the most points then. Okay. So don't get hyperfixated on your graph being perfect. It's much better if it isn't. Okay, maybe yes.
Do you always do a slant?
No. Well, how do I say this? If I have a rational function, then there will be some kind of end behavior, which we call horizontal asymptote or slant. So there's three situations, and one of them is the slant, yes. So I could say, given a rational function, you will either have a flat horizontal asymptote or a slanted horizontal asymptote, right? Now, okay, let's do this. Let's graph this real quick, see what it looks like, and then we'll move on. And I'll use Desmos. Why not? I'll make it quick. Okay. What was this again? It was x cubed minus 1, x squared minus 16, right? If we pull out a bit, there. And then if I put in here also x equals -4 and x equals 4, there's my vertical asymptotes, right?
Mm-hmm. And then y equals x. Right?
You guys see that okay? Does it basically match up here?
Mm-hmm.
Now look here. So see what it's doing? So it actually goes through this and goes closer, but I don't want that kind of detail. This is beautiful by hand, but there's no way we can know this kind of detail. Does the shape match our shape? Are things in the right place? Yes, that's all that matters, right? Let me see if I can change one little thing here. Let's see if I don't know if I could do this on the fly. Maybe. Okay, that's just weird. Where's everybody? Oh, they're way up there. Okay. No, it's not. It's too big of a change. Sorry. I don't play around with this too much. Okay. One thing I could do is this. Let me see what happens if I do this. Same idea. Oh, that's right, because it's not big enough, Jeff. No, it's not a big enough change. Oh, yeah, beautiful. All right, real quick, guys. Do you see how here, this is up here, yes?
Mm-hmm.
Right, do you guys see that? Now, watch. I'm going to do something so that the x-intercept is actually here. And the way I do that is to make this 125, because the cube root of 125 is 5. Now, do you see how it moved down here?
Mm-hmm.
You guys see that? Here. This is no longer up here, it's down here. Do you guys see that? So it could either be up here, or it could be down here. And one big way I tell is, where's the x-intercept? If it's there, like I just forced it to be, now it's going to be down here. And you can see that it's down there. It's a little, it's a little extreme. If I zoom in a little bit, it might look better. Wee-haw. So now it's down here instead of being up here. Okay, maybe. Notice the middle became parabolic because now it doesn't have an x-intercept to go through, right? Let me go back to this. Let me put in one more thing. Let me put in, Jeff. Let me put in y equals x. This is our slant asymptote. Do you see what it's doing at the extremes? Isn't it approaching that line if you let time go on? You guys see that? Okay. So that's the idea of any asymptote is over time the function should get closer and closer to it.
How do you know when you have like only one x-intercept or two x-intercepts?
Oh, well here, again, we have 3, but we only care about the real ones because we're only doing the real slice. Yeah, so here I know I've only got 1 because the other 2 are complex. So if I have any sum or difference of cubes, there's just going to be one real solution that I have to worry about. The other 2 are guaranteed to be complex. That's kind of a good note to remember. Okay, I like it. Okay. So just be real careful. I mean, I can't blame you that much if you get a problem. The first thing you do is graph it, but trust me, that is the worst. Because you will invariably do something that you should not know. Does that make sense? So try desperately to do everything. And then if you see a major mistake in the graphing calculator and you're running out of time, do not erase your graph. Leave it. Because it matches your work. Right? That's what's more important. You can put a little note saying, I know this isn't quite right, but I don't see why I ran out of time or something. Beautiful. You're going to lose some points, but nowhere near as many if your graph is suddenly beautiful and your work wasn't. Yes?
Where did you graph the y-intercept at?
Oh, here.
Oh,
Yeah. It was 1/16.
which is like a really tiny decimal.
True, but what's the most important thing is it's positive. If that y-intercept would have been negative, do you guys see how it would have gone this way instead? If I put that y-intercept there, it would have gone this way instead. In fact, I can do that really easily. People at home are missing what I just did, but if I make the y-intercept negative, and I could do that just by making this +1. Did I do it? No. There you go. Do you see now it's going this way? Well, actually, it's doing the same thing. What does it do? Let me zoom in. Oh, there it is. Okay. Oh, of course, I'm being silly. Because I changed the x-intercept and that. There's no quick way to do that. Sorry. I was hoping there was a quick way to do that. On this one, if I change this to a +1, not only do I change the y-intercept to -1/16, but I also change the x-intercept. So that's why it's got the same shape. But yeah, if I would have done all the work, and this would have been, the y-intercept would have been here, it would have gone like this. Okay. Yes?
And how would we know? If that makes sense.
How would we know what?
Would it just be determined on if it's positive or negative? Like which direction?
Two things told me what this looked like in the middle. The location of the intercepts and the fact that this had an odd multiplicity.
Okay.
If this had an even multiplicity, it would have touched and keep going up,
Okay.
right? Does that make
Got
sense?
it. Yeah.
Even means it turns, odd means it goes through.
Oh, right.
So the fact that the intercept was there and this intercept was there and I go through this, I knew exactly what that looked like. I don't need any more points to help me. If I let you do like 3 points, you can figure out what f of 3 is and see that it's up here. And that'll give you a better idea what it looks like.
So we just look at the first one to decide the end behavior?
Say again?
Do we look at the first one, like how you just looked at x minus 1? Do we look at that first one to see our end behavior?
Remind me, guys. End behavior for rational functions. What's the other name for that? Horizontal asymptote. Right? End behavior just means what's happening when x gets really, really big. That's all end behavior means. So how does that translate to rational functions? If I let x get really, really big, what's it doing? It's a horizontal asymptote idea then, right? Or in this case, slant. So real quick, I don't know if you guys noticed, but if I make this a 4th power, it's a little gross because it's way up here. Do you guys see how this is not easy to see? It's just something I could do to make this a little better. I think so. If I make this, that's a little better. Okay. If you did long division, can you guys see how you would have an x squared left?
Yeah.
So the end behavior would be parabolic. You guys sort of with me? So do you see how the end behavior, it's sort of like a parabola, if you just look at the ends? Okay. So that's how you could have a slant asymptote that's actually parabolic. Okay. I went a little far there, it's too bad. Okay. So again, you gotta get in there and try these out. Try these problems out. And you just, the more you can break up, vertical asymptote consideration is its own little problem. Factor the bottom, you gotta remember it's the bottom because it's the domain. What causes domain issues in fractions? The bottom, right? Bottom can't be 0. Vertical asymptote, all about the domain. What can you not use? So I'm gonna put a wall there. You guys with me? I'm getting so much side eye, it's crazy. You know, like, it's like that meme of that little puppet. Yes?
If this is an after class question, that's okay, but I was wondering how we would take a table and put it into an exponential function, like make the function.
Oh, okay, so that's like from chapter 6, okay.
Yeah.
Okay, anything else about this here? Yeah,
Sorry, what?
we'll get there, sorry.
long divide again?
Say again?
Why did we long divide again?
So, let me see. When x gets really, really big, okay. Hold on. Everybody's got what they want from this, I'm sure. Okay. Which way am I pointed?
Look at this. Look at this equation. I just saw this.
We'll get to that question, Hannah, sorry.
Okay, I didn't even know I was ahead.
You're good. Is everybody cool with this? If x gets really big, the bottom's going to overwhelm. If I divide by bigger, it goes to 0. Is everybody cool with that situation?
Yes.
That's definitely going to 0. If I have this situation, now the two are more lockstep. Neither one is growing that much faster than the other one, but the top is always 3 times bigger than the bottom, correct? You guys see that?
Yes.
When x gets really big, these things don't mean shit, no offense. And then the top is 3 times bigger than the bottom. So when x gets really, really big, this function should go to 3. Hey, you found us.
Yes.
Okay. You everybody with me so far? Now, in this case, if I make the top bigger than the bottom, now it's a question about if x gets really big, what kind of is left alive, right? So it might be better if I do this. If I have this, okay. So you have this function here. When x gets really, really, really big, what does this piece do? When x gets really, really, really big, what's growing faster?
Oh,
The
The
bottom.
bottom. So this is going to go to, because we're in this
0.
first situation, correct?
yes.
Mm-hmm.
So if I have something written like this, I can immediately tell which piece is going to dominate. The fractional piece goes to 0. This piece dominates.
Mm-hmm.
X plus 1 minus really tiny shit, yes?
Yes.
Mm-hmm.
I like it. So it's like 1,000,000,001 minus 1/1000,000th. Okay, I can ignore the 1/1000,000th, right? You guys kind of with me?
Yeah.
Okay. So if I have something that's not written like that yet, for example, if I have the problem we had here, which was this, then I want a long divide so I can see what's the dominant piece. I gotta see what the whole part is. You guys cool with me saying that? This is like a whole number, fractional number, correct? If x is 7, this is 8 minus some fraction, yes?
Mm-hmm.
So it's the whole part and a fractional part, yeah.
What does the leftover whole part do? What do we do with that?
It's what this function is when x gets really, really big. So let's try this. Let's remind you guys something about the calculator. Which way am I
What's
facing?
that? Sorry.
Say again?
What's the one you just wrote?
That's the problem we were working on earlier.
Oh, okay.
Yeah. That's the one we graphed. So just remind you guys how you can use your table. In your calculator. And then we desperately got to get in chapter 6. No, I don't care. Okay, that's great. Okay. So let's put this function, where to go? X cubed minus x cubed minus 1 divided by, thank you. So if I go to, if I change my table to ask,
Wait, how did you get there again? The table set up?
second window
Okay.
says table set,
Okay.
and then I can change it to ask. So now if I go to my table, I can just feed it stuff. So, horizontal asymptotes, remind me, what are they all about? When do they kick in? When x
Gets really big.
gets big. So let's do that concretely instead of abstractly. Let's throw some big ass x values in. So let's start kind of small big ass, like 100. Everybody agrees 100 is a decently big number,
Yes.
but in the grand scheme of things it's very small. But let's try 100. Interesting. I should have started with 5. Let's start with 5. Okay. And then we go to 25. Already you can see the output looks to be roughly equal to the input. Yes? Do you guys agree?
Yeah.
Not when x is small. When x is small, is the output equal to the input?
No, it's far.
But the bigger the input gets, oh, look at that. Now the calculator's like, dude, it's basically the same.
Okay.
Now, real quick, it's not exactly 1,000. It isn't. But it's 1,000.00003 or something silly. You guys understand what I'm saying? So it just kind of rounds it. What did we get as the slant asymptote for the one we just did?
Y equals X.
Y equals X. When X gets really, really big, the output's going to equal the input, or close.
Okay.
You guys see that? So we saw that graphically. We saw it approaching Y equals X, and you can see it concretely. So then you could also put negative shit in there, right? Because it's supposed to happen negative stuff. You can do it here, Jeff. There you go, buddy. -5. Okay, no good. -10. Better. See that? Already. -50. Okay, there. And then if I do -500. All right, so now it's the same. So if I long divided, got 2x, I could go to my table, and 100 would be like 200 point something. If I let my inputs get bigger, this will tell me what the outputs do. Yes?
Just out of curiosity, what kind of situation would you apply this in real life? Like, what kind of situation, what kind of job?
Oh, business, science, it's actually silly. I want you guys to understand, even at the level of pre-calculus, you are still learning tools. You are in the process of tool learning. You are all learning tools to use. And your question is, where do I use these tools? Almost freaking anywhere. Any job in which you could set up an equation, and that is more than you realize. Trust me. My little brother does sound design for plays, and I use him a lot when I'm teaching. Well, later I'll talk about him when we're doing trig functions. Because when you're doing sound design, you got these, and I don't know if anybody in here plays any musical instruments, may have an amp, and you turn the gain up too much, and it gets cut off at the top and so forth. I mean, so that you can actually see that with the sine wave. You can actually see that with the equation that you can set up. So the more you can work with the math itself, the more you know how to set things so you get the best possible sound output. So Timmy, all of a sudden, my little brother, appreciated math a little bit more later in life as he's working more and more with these sound design. Same with my other little brother, James. I'm going to use him too because he hated math. And then he started doing survey work. You know, the guys that you'll see them looking through the thing and they're just seeing how much the ground has changed. They use the shit out of trigonometry. So later we're going to learn cosine, sine, all that kind of stuff. And holy shit, that entire field is nothing but trigonometry. Right? So the more you understand trig, I know a lot of their things, they have it built in, but the human has to understand some of the tricks so you can know when something's not quite going right. Anyway, sorry. Thank you. One of my favorite questions, and you know, normally it's the worst question, is when am I going to know how to quadratic formula by lettuce?
I was trying not to ask in a
No,
challenging way, because that's not
No,
what
I've had the people that are like, when do
Yeah,
you
I
use this
know.
shit, Mr. Wall? I'm like, good lord, dude.
Yeah, I know, there's like totally people like that.
All right. The most important time is now, right? Test coming. But I appreciate, I mean, in general, yes. Okay. Real quick, what would happen if let me clear this thing real quick. I think the quickest way to do it is this way. Is that clear, Jeff? I can't remember. Shit. Playing around too much. Yes, okay, good. Real quick, if I put actually I'm gonna put it down here. If I made this cubed, and I put 2 here. Can anyone tell me what the horizontal asymptote would be?
2.
No, careful.
1.
1 over 2.
2.
Remember, when they're the same degree, it's the ratio of the leading coefficients,
Okay.
right? When x gets really, really big, The only things that matter are x cubed over 2x cubed, and that's 1/2. So you can, again, you can go to the table, put in 5. Okay, that's not very, well, it's already 1/2. That's hilarious. Put in 50. See how it's a half?
Mm-hmm.
Now it's just going to be a half forever. Yes?
Is it the same as the g of x, where 3 is big? They're both the
Yeah,
same?
this one, yeah, so if I put this function in, I would get 3's out eventually. When I put bigger x's, the outputs would eventually just always be 3. And again, it isn't really 0.5, it's just rounding it, but it's like 0.5000003 or something. It never gets to 0.5, but it gets so close, the calculator's like, dude, it's 0.5. Okay. Maybe, yes.
So if the degrees are the same, then you divide the coefficients.
Yes, so either the top degree is smaller, so it's 0, goes to 0. The x-axis would be an asymptote. They're the same degree, in which case you divide the leading coefficients, and that would be the asymptote. Or the top degree is bigger, where you have a slant asymptote. I like it. You guys with me?
But if the top degrees are the same, it's still horizontal asymptote.
If the degrees are the same, on top and bottom is horizontal asymptote.
Okay.
Yep. Okay. All right. So,
Oh yeah, 'cause you're trying to get that.
closing the door on chapter 5 for the moment. We're going to go into chapter 6 now.
So there's like 5.7. I don't know what the rest of the ones are for 5, but like all
Here,
of
let's
them are
take a
like
look.
review stuff. Yeah,
So just reminding you guys.
5.6 and 5.7.
5.7 was
kinda like-
inverses and radical. We actually already talked about those, right? How to find inverse functions. We talked about radical functions. You guys all with me?
Oh yeah. Okay.
All right. So for example, let's look at a few
Okay. So
problems.
yeah. So that is just like review.
We talked about a restricting domain. So here you can see there's the inverse idea, right?
Mhm.
So 5.7 should be kind of a nice little breathing spot where you can, this should be old stuff. Find the inverse of functions,
Yeah,
right?
yeah.
Graph them, okay.
Yeah.
I do kind of like that the review inverses because we're about to do a lot of inverse stuff in chapter
Oh yeah.
chapter 6. All right, enough scrolling through the book chapter. So, sorry. The way I normally try to introduce this section is we have seen examples where the variable is has a power on it. We've seen examples where we put a variable on the bottom, right? We've seen examples where we put variables inside various functions, right? Absolute values, square roots. There's one major place we have yet to put a variable in, and that is in the exponent itself, correct? So we haven't looked to see what would happen if I let the exponent I'm raising to change. I love you guys. All right.
See, that's what was getting me good. I was like,
All right. So when you first are given, what do you do besides cry a little bit and find somebody to hold on to? When you're given a function, you're not sure what it looks like. So let's look at a function 2 to the x. This is an exponential function because math people are very creative with their naming, and we said the variable's in the exponent, let's call it exponential function. So again, that's the drunk history of it, but it's not too far off, right? You guys all with me? So this is called an exponential function. Can you guys kind of already tell that this sucker's going to grow fast? Has anybody ever watched any horror movies or like, I know we just went through a pandemic, so these kind of movies mean a lot more to us now, but the old virus movies.
Yeah.
And at some point in those movies, somebody says, it's growing exponentially.
yeah.
Has anybody ever heard that?
Yes.
Now again, I'm going back to the blob again, because it's growing exponentially, because what the shit does that mean? So let me ask you this. Has anybody ever heard this old riddle, or not really riddle? Would you accept $500,000 from me, or would you rather have 1 penny today and then I give you double that tomorrow, and I continue that for the next 30 days?
Second option.
You've heard it before, right? Okay. When you double something, even if you started at a penny, If you do it over 30 days, you're gonna end up with a shit ton of money, right? In fact, let's try that out real quick. So that's basically this. I want you guys to see why it's this. So on day 1, day 0 we'll call it, right? Day 0. How many cents do you get? 1. The next day, 2. 2 cents, right?
Mhm.
So if I cut to the chase and do the 30th day, well, this will be the 31st day, but that's all right. We'll go with 30, a month with 31 days, so I'll do it for a month. What's 2 to the 30th power? My hand still doesn't do that for me.
No, but the 10th is 1024.
True. So now just do to the 30th power. Can your calculator handle that? I can't remember. Yes. What do you get?
107
What, 107?
3741 824.
824? That's cents, correct?
Oh, yeah.
You with me? So I'm going to do this. Is everybody cool if I do this? Now it's dollars? If I just move it back twice, it's dollars now, right?
Uh-huh.
Right? Everybody with me?
Mhm.
How much money is this?
10 million.
10 million! So I offered you $500,000 now, or 1 penny today, and I'll double that tomorrow for the next 31 days, right?
That's crazy.
Do you guys all understand?
Yes.
This is weird. This is weird. I can't remember this, but I gotta look this up, and I forgot to look it up. If you fold a piece of paper over a certain number of times, it will reach to the moon. Every time you fold a piece of paper over, aren't you doubling its thickness? Think about it, right? So every time you do that, you're doubling it. So if I double it so many times, it's gonna reach really far up. Now, of course, you gotta start with a gigantic piece of paper.
Like Mythbusters.
You've also got the thing about you can only fold something 7 times, which, like Rick and Morty played with for a little bit, right? Back in the day when, well, at least they got rid of it. Anyway, enough about that. All right. This is a good example of mathematical functions doing things we're not hardwired to understand. You guys, if you never heard of that before, you would never have picked the option of a penny today, double it tomorrow for the next 30. There's no way in hell you would have picked that option. And I can't blame you, because this stuff is not hardwired in our brains to understand what that will do. It will grow stupid fast. So if I square something, what is 30 squared? You could do it. 3 squared is 920, so 900. Now compare to raising 2 to a power. Oh, holy shit. So 2 to the x will grow so much faster than x squared will. Are you guys sort of with me? Okay. All right. So in terms of what this function looks like, have I investigated enough numbers to know what this graph is going to look like? What x values have I not looked at all yet? What kinds of inputs have we not looked at all? Negative. So let's try some negative inputs. What is f of -1?
Wait.
2 to the -1, right? What's 2 to the -1?
1 over 2 to the
What's a negative power mean?
1 over 2.
Flip.
1/2.
So 1/2. Sorry, I know some people are saying 1/2. I'm sorry. I just want to make sure everybody's on the same page. You guys all with me?
Mm-hmm.
So the funny thing is, if 2 to the first is 2, 2 to the -1 is 1/2. What's 2 squared? 2 squared, 4. So what's 2 to the -2? 1/4. You guys see the connection? It's beautiful. So f of -2 is 1/4. F of -3, 1/9, 1/9, 1/8. Good Lord, Jeff. And you keep going. Every time you go, it's cut by half. You with me?
Mm-hmm.
Will it ever get to 0? If you cut something in half forever, will it ever get to 0?
No.
Nope. You get really, really close to 0, correct? So help me out. Let's see if your calculator can do this. What is f? What is 2 to the -30th power? I don't
1
know.
over whatever that number is.
Hey, good. I don't know if your calculator's going to be able to do it. What did it say?
It's 9.3312257 times 10 to the -10.
So it's
Oh, it did it.
0.02, 3, 4, 5, 6, 7, 8, 9. So it's that.
Yeah.
Roughly, with some other numbers after, right? Do you see what I'm saying? So it's gonna get stupid small, but it's never gonna get to 0. What does it sound like? It never gets there. What's it sound like?
An asymptote.
Asymptote. It's always getting closer. Every step it takes, it's half as far away as it was before, but it never gets there. So we can kind of graph this thing now. Well, we can totally graph this thing now, but oh, there's the clock.
It's 10:30.
I don't like it in here better.
What's up?
Said I like it in here better a little bit.
Me too. It's just bad in the summer, and it's bad that people are in here Tuesday, Thursday, so we can't keep it. Yeah. So the main ones I always plot are 2 to the 0, 2 to the first, and 2 to the -1. 2 to the first is 2, 2 to the 0 is 1, 2 to the -1 is 1/2. Do you see if it was 3 to the x, it would be basically the same, except this would be a little higher and this would be just a little lower, because 3 to the first is 3, 3 to the -1 is 1/3. But it's always going to have the same shape. So it's going to go insane on that side, and it's going to go really close to 0 on that side. Asymptotic. Whee. So exponential functions will have this shape. Right? Yes.
You can tell me if this is going too far, but there was an equation that kept popping up in the homework that I was just like, what the heck?
Okay.
It was P.
Oh, yeah, okay.
Yeah.
So,
You knew me.
there are applications of exponential functions, and one of them is interest.
Yeah, interest, yeah. I was trying to look up maybe some videos on maybe how I could but everything they were saying, I was like, we haven't covered any of this, so I just thought.
Yeah, no, we hadn't gotten to chapter 6 until just now.
Yeah, I didn't know that, so I was just like,
Let me see, I didn't really, I forget which one they used.
This is
Did
like
they use
end
1 plus
of
r over
6.1.
n to the t?
yeah.
Yeah, so
Yeah.
for interest, actually it would be that, yeah.
And I think
Whoa.
there was like a parenthesis and an exponent.
So I've got a whole thing we're gonna kind of step through to make sense of this equation. Because if I just plot that equation up there, you're all like, okay, it's a bunch of shit. What's my input variable? What do you guys think? This is not the easiest one, but if it isn't x, very often it's t. So t almost always means time. So if I put, means principal, if I put a certain amount of money in at a certain interest rate, and it's compounded a certain number of times a year.
What does that mean? Sorry to interrupt you.
No worries.
I have no idea what it means.
Yeah, I don't.
So do any of you have savings accounts?
Mm-hmm.
I understand if you don't. I understand.
Sort of.
Trust
yes.
me. I understand.
I think so.
I know I learned all this, but I forgot.
If you have like a 5% interest account, normally it's a simple interest, and they'll do that every year.
Right.
In which case, n would be 1, because they would add interest. Now sometimes you do have interest accounts where they add interest every month. So then n would be 12, because that's 12 months in a year. So they do it
Okay.
12 times each year. You guys see it?
Okay.
So wouldn't you want it done more often? Because the minute they do it, there's more money to grow for the next time. So they only do it once a year, you get added, and then the next year you can grow on top of that. If you do it every month, you got more money that'll grow next month, get more money, that'll grow next month, get more money, that'll grow, so forth. And there's the old adage, you gotta have money to make money, right? Okay. Does it make any more sense? So
Isn't interest bad? Not
no,
adding money?
if you borrow money,
Oh.
interest sucks.
Oh, okay.
If you save money,
Then
you
you're
won't get an
gaining
interest
interest.
rate.
Okay.
Yeah, exactly.
Okay.
All right, guys. So next time we'll do a little bit of that. I really hate
Sorry,
business.
I
Business is my least.
brought it up.
Me
Interesting
too.
subject.
My dad literally will be sitting next to me doing the taxes on the computer, and he'll be like, "So this is why we do this." And he's an accountant,
that's
so
why you
he's
just
like,
uploaded
so
TurboTax,
he's like,
Shawnee.
he's like